Hi again. Welcome to the second video in this short series on the fundamentals of how computers operate. My name is Joe Hawking. So in this video, I'm going to be demonstrating something called logic gates. As you can see, I just have some batteries here, some wires, LED, a little light bulb. Logic gates are circuits made with wires and switches that have a predictable pattern of inputs and outputs. And that notion of predictable pattern really gets at why they're useful for doing computing. They're predictable, so whenever you have one input, you're always going to get the same output. Meanwhile, their pattern, it's not just a single input and output, but rather, depending on what inputs go into the logic gates, then you get different outputs. Now, on the level of a single logic gate, those inputs are still pretty simplistic. They're pretty primitive. But you can combine these logic gates, and then the whole arrangement, the whole collection of multiple logic gates allows you to have much more complex inputs and outputs. And that, if you think about it, is certainly one way of thinking about a computer. It's a series of, like when you give the computer a series of inputs, the computer has a series of outputs. So I'm just going to be refocusing the camera down on the table so that you can watch me just hooking together some wires and making a logic gate. Great. These are just two AA batteries in a AA battery holder. When they're side by side like this, that's 3 volts, since each one is 1.5 volts, and when they're side by side like this, that just adds up, which is perfect, since this LED, this is rated for 3 volts. The longer prong, it's got 2 prongs, a positive and negative side. The longer prong is the positive side. So, all right, so just to demonstrate that the LED works, then the first step, I'm just going to wire it directly to the positive and negative ends of the battery, and you can watch the light turn on just to verify that the LED works. So, boom, great. There we go. Okay. So now, just to complicate things very slightly, I'm going to add a switch into the mix here. Now this particular switch, it just has these little 1 and 0 indicators on it. You can see when it's set to 0, that means the switch is off. When it's set to 1, that means the switch is on. So great. So we'll put that in here, and I'll insert another wire in here just basically so that I have something to hook the switch into. So, all right, I'll clip that. Clip that. Clip that. And finally, I'm going to clip that. And you can see now the light is off. The switch is off. It's in the off position, so when the switch is in the on position, the light turns on. Great. Not complicated. Okay, now this is the first place where I'm going to be doing something that seems a little weird. So, because now, instead of having the switch turning it on and off directly like that, I'm actually going to put the switch in the middle. And I'm going to show you how that works and what's going to happen. All right, so I got another wire in here. Now, what I'm going to do, even though the length of the wires makes it look like the switch is out here, I mean, in terms of if you actually see where the wires are going, you can see it's almost like the switch is in the middle in between these. But anyway, I'm providing an alternate path here for the electricity to go. Turn that on. Now, currently, as you can see, the switch is in the off position, and the light is on. The switch is off, but the light is on. Now, watch what happens when I click the switch on. The light turned off. When the switch is off, the light's on. When the switch is on, the light goes off. Now, that's a little weird to understand what's going on, so let me explain what's happening. Electricity, it goes through the path of least resistance, which means that when the switch is off, there's only one path it can go through, which is through the light here. And so it's going to turn on the light. It's going to go through that path. But when the switch is on, now there's another path the electricity can go through. And this other path has less resistance on it because, there's no light. So all the electricity is going to go through this other path. The electricity always takes the path of least resistance. Since no electricity is going through the light anymore, the light turns off. Okay? That's still one switch and one light. One input, one output. I'm going to add a second input in here. I'm going to add a second switch, just to complicate things. All right, now we have two switches. And let's see, I'm going to have both switches in the off position. Oops, that one fell off. Whatever, I'll put it back on. So. All right, so right now, both switches are off. Both switches are in the off position, and you can see the light is on. Now watch what happens if I flick one switch. This we'll call switch A, and we'll call this switch B. If I flick switch A, nothing happens to the light. The light stays on. Okay, so switch A is on, B is off, and the light is on. Okay, now I'll do B. Switch B is on, switch A is off, the light's on. Okay? Now though, look at what happens. If I switch both A and B on, the light goes off. Okay, I'm going to do it a second time, real quick. You can see. All right, so we saw, when we built out the actual circuitry, we saw flicking switch A and flicking switch B in different patterns had different outputs. So I'm just going to write a diagram showing that. So switch A and switch B. So the first thing we saw was if both are off. So switch A is off, that's the input to switch A, and switch B is also off, that's the input to switch B. And in that case, we saw that the output, the state of the light, was on. The light was on if both A and B were off. Now we also saw then in the switches, I flicked on switch A. So A was on, B was still off, and we saw the light was still on, so the output was still on. Then when we reversed the switches, still had the same effect. Now switch A is off, but switch B is on, and you can see the output was on. But when we switched both switches on, both A was on and B was on, then we saw the output was off. Now this pattern of inputs and outputs, this is the NAND gate. NAND, that's kind of a weird name. The N stands for not. So this is actually a short for not and. So to help explain that actually, and it makes sense, A and B are both off, so it's off. In this case, A and B are both on, so it's on. And then in this case, what's going to happen is it just says if A and B are both on, it's going to turn on. But since
it's not the case that both A and B are on, only one of them's on, then the output will be off, and same here. And then not AND is simply just take all the outputs from AND and reverse them. So every time you see 0, it's a 1. Every time you see a 1, it's a 0. So there we go. So NAND.
Alright, so now you know how logic gates, like NAND, are wired. However, it's still unclear how logic gates connect together. And the key to that is what's called electronic switches. And that's the topic for the next video.